A long time ago, in a math class far, far away, the teacher hadn't prepared to teach. So what does a teacher do when they're not ready to teach? They give a really hard quiz that they figure this will take the students a while. I can read my notes, figure out what I'm going to do today. So this teacher walked into the class and he gave his class a really hard quiz. And the really hard quiz was add 1 plus 2 plus 3 plus 4, keep going all the way up, plus 98 plus 99 plus 100, add those all together. And you're not allowed to use a calculator because this was back before calculators were available. Sigma thing, I don't know what sigma thing is. I know what you mean, but that's not what we're going to do. We're not going to do this. That's a series, by the way, not a sequence. But anyway, so this teacher thought he was pretty clever. He thought, that'll take 15, 20 minutes all time to get ready to teach. Unfortunately, there was one really, really smart student in the class, and he had the answer in about 30 seconds. It's bigger than 1,000. It's smaller than 10,000. It's somewhere in between. 5,000 is pretty close.
Wait, isn't it 54321?
Blast off? I don't know what 54321 is.
5,431.
No, it's not 5,431. All right, so anyway, what this really, really smart person did is he said, I'm going to write it backward. So he wrote 100 plus 99 plus 98 plus 3 plus 2 plus 1. It's not 5,001. And then he added, what's 1 plus 100? 101. What's 2 plus 99? What's 3 plus 98? So then he had a 101 and a 101 and a 101. So then he did, how many 101s are there? So he took 101 and multiplied by 100. And then you have to divide it by 2. Why do you have to divide it by 2? Because you did it twice, didn't you? So that was the really clever person's answer. So 101 times 100, how do you multiply by 100? You just move the decimal. So that's 10100. And then divide it by 2. 10 divided by 2 is 5. And 100 divided by 2 is 50. So the answer is 5,050. 50-50. Anybody know who the really, really clever person was? No, a couple people say that before. It was not me. And I was not the teacher either, by the way. I prepare for my classes. It was not Jay either. It was a long time ago. Abacus is here. I did not use an abacus when I was a kid. I did use a slide rule though. What's that? Good question. Whole other story. No, the person's name was Frederick Gauss, the famous mathematician who lived a long, long time ago. I don't think there was 1600s.
Oh, I thought you meant like
So now the deal is there anything special about the number 100? If the person had asked 1 plus 2 plus 3 up to 10,000, could you do the same thing? Yeah, you could, couldn't you? All right. So there's a branch of mathematics called number theory. And number theory has all sorts of formulas like that. So the formula we just did, if I take 1 plus 2 plus 3 all the way up to 100, it looks like what I can do is I can take 100, multiply it by one more, 101, and then divide the answer by 2 and I'll get the right answer. And so in this branch of mathematics called number theory, they investigate these kind of patterns and then they prove that it doesn't matter what number you use for n, that formula is always going to work. And one of the techniques they use is what's called mathematical induction. So that's what we're going to do today. We're going to prove things by mathematical induction. Mathematical induction has 3 steps. Step 1, prove the statement is true for n equals 1. So, in other words, if n is just the number 1, then what do I have on the left-hand side? Just 0 and 1, which would be 1. So it is 1 equal to, if I take 1 and plug it in here, I have 1 times 2 over 2. Are those equal? Yes. So that statement is true when n is 1. So you prove that it's true at the first step. 2. Assume the statement is true up to some value k. In other words, for this problem, we're going to assume that 1 plus 2 plus 3 up to some number k is equal to k times k plus 1 over 2. So far, we know it's true up to the number 1, don't we? We prove that it's true up to 1. We're going to assume it's true up to some other number. And then step 3, prove the statement is true for k plus 1. So here's what's happening. It's kind of like knocking down dominoes. You line dominoes up in one big line and you knock them over. What happens when you push the first domino? It knocks over the second domino. What's the second domino do? Knocks the third domino. So this is what we've done here. In the first step, we've pushed over the first domino. And then what we're assuming in the second step is we're assuming the dominoes keep knocking each over for a while. So we're assuming that it knocked over up to maybe domino 97. I don't know what k is. K is just some number, up to 97. And then we're going to show that domino number 97 knocks over domino number 98. And that's called proof by induction. So since we knock over the first domino, these two statements together, when we're all done, we'll say, well, that knocks over the second domino. Once we know we knock over the second domino, these two statements put together would say, okay, you knock over the third domino. And it keeps going, and when does it stop? Never. So we have an infinite line of dominoes that keep falling. That'd be pretty cool. All right, so what I have to show is I have to prove that 1 plus 2 plus 3 up to k plus k plus 1, I've got to go one more step, is equal to, what happens when I plug in k plus 1 on this right-hand side? Instead of k, I'm not going to have k, what am I going to have? If I'm plugging in k plus 1. I'll have k plus 1. And then instead of k plus 1, I'm plugging in k plus 1. So if I plug in k plus 1, what's k plus 1 plus 1? K plus 2. So that's what I need to prove is true. All right, so here's how we do it. 1 plus 2 plus 3 up to k plus k plus 1. What can I say about 1 plus 2 plus 3 all the way up to k? How much is 1 plus 2 plus 3 all the way up to k? It's not k. It's not k plus 1. Look up above. How much is 1 plus 2 plus 3 all the way up to k in step number 2? We're assuming that it's working all the way up to here. So 1 plus 2 plus 3 all the way up to k is k times k plus 1 over 2. So this whole block here, I'm going to replace by k times k plus 1 over 2. But then I still have this little k plus 1 stuck on the end. So this whole block became this piece, and then I still have the k plus 1. All right, so what I want to do is I want to add these two things together. How can I add these two things together? I need a common denominator. What's my common denominator? 2. So I think of this as being over 1, and then I have to multiply the top by 2 and multiply the bottom by 2. All right. So that's k times k plus 1 times 2k plus 1. I wrote it wrong. Let me write it over again. I said the right thing. I wrote the wrong thing. That's k times k plus 1 plus 2k plus 1. Notice I left my parentheses there. And I did that for a good reason. Because I wanted to. The reason I did not distribute that 2 through, which of course you could, is I wanted to have this k plus 1 here and that k plus 1 there. What can I do on the top if I have a k plus 1 there and I have a k plus 1 there? K plus 1 is what? It's not squared. Because they're not being multiplied together, are they? I could distribute and make 2k plus 2. What if I had, let me go up here. If I gave you ky plus 2y, you could factor out a y because y would be the common thing. And what would be left over? K plus 2. Same deal here. I've got a k plus 1 in this term and a k plus 1 in that term, so what can I do? I can factor out the k plus 1 as the common term. When I factor out the k plus 1, what's left? And what's left over is k plus 2. And then the whole thing is divided by 2. And that's what I wanted. I wanted that to happen. We haven't done anything like this in this class before. I don't know if you've done this.
Not like this.
It's like a proof in geometry, correct? So proofs are kind of weird and kind of hard because most of the time when you're doing math problems, you're working it out and your answer is a number, or your answer is a function, your answer is 12, or your answer is 2 cosine x. But here your answer isn't a number or a function, it's a bunch of steps written out. So proofs are kind of weird. All right, so let's try the next one. So here's kind of a weird rule. If you add up all the numbers, 1 plus 2 plus 3 all the way up to n, you get n times n plus 1 over 2. In problem 2, we're saying, what if you only add up the odd numbers? 1 plus 3 plus 5 up to some odd number. You happen to get n squared. Kind of a weird thing. I mean, let's just try it. What's 1 plus 3 plus 5? 9. Is that a perfect square? Yeah, it happens to be 3 squared. And how many numbers, when we did 1 plus 3 plus 5, how many numbers did we add? 3, and we got 3 squared. What if I do 1 plus 3 plus 5 plus 7? 16. And that's 4 numbers, and 16 happens to be 4 squared. All right, kind of a weird pattern. So we're going to prove by induction that it's true. To prove by induction, we do 3 steps. Step 1. N equals 1. So you prove that you can knock over the first domino. If n equals 1, what do I have on the left-hand side? On the left-hand side, I would just have 1. And what would I have on the right-hand side? 1 squared. Does 1 equal 1 squared? Yes, so that's true. Step 2. I'm going to assume 1 plus 3 plus 5 plus, up to some point, 2k minus 1 equals k squared. So that's step 2. Just assume that. Step 3, prove 1 plus 3 plus 5 plus up to 2k minus 1 plus, and then I go to the next step. So this one ends at k, so the next one's going to end at k plus 1. So I'm going to have 2 times k plus 1 minus 1, so I plug k plus 1 in over there, equals, and I plug k plus 1 in on the right hand side. Missing a parenthesis. What are you lost on? How many steps did this one have? It had, but there's really only k steps. For example, like when I did 1 plus 3 plus 5, k would be 3. I did 1, 2, 3 steps, and I ended up with 3 squared. So here, there are k steps, so I'm stopping at k. So at my next step, I got to go one more. So I have to go k plus 1. So I take k plus 1 and I plug it into this formula on the left-hand side, and I take k plus 1 and plug it into the formula on the right-hand side. I got to go one more past where I ended up. I ended up here at 2k minus 1, so I've got to go one more step, which means I've got to go up to k plus 1 steps, and I plug it in on both sides. All right, so again, I take this first big block that I have. There's that first big block, and I use what I have in step 2. That whole first big block, what is that? That's k squared. So that whole first big block, that's just k squared. Plus. All right, any ideas what to do here? I have to rewrite this because it should be 2 times k plus 1 minus 1. I had it written right the first time, and then I changed my mind and I rewrote it. It should be that. So I think what I would do there is I could do a little distributing. So that's 2k plus 2 minus 1. So that's k squared plus 2k plus 1. What can I do with k squared plus 2k plus 1? I can't take out a k because there's no k over here. I can factor though. It factors as k plus 1 and k plus 1, which happens to be k plus 1 squared. And that's exactly what I wanted it to be. I wanted it to be k plus 1 squared. I don't know. Let's try the back. No. If I asked you to use induction to prove, then I promise you that it really is true. I won't give you any false ones and try to trip you up, I promise. That would be really mean. I won't do that. All right, so again, look at what we did. First, we added up all the numbers. When we added up all the numbers, we got a formula. Then we added up only the odd numbers, 1 plus 3 plus 5, we got a formula. Now what are we doing? We're adding every third number. When we add every third number, hey, we get a different formula. All right, so what's step 1? Show that's true for n equals 1. True for n equals 1. Well, when I plug 1 into the left-hand side for n, what do I get? I just get 1. Equals. What do I get when I plug 1 into the right-hand side? 1 times 2 over 2, which happens to be 1. So we can knock the first domino over. It's true for the first one. What's step 2? Assume that's true up for some number. So assume 1 plus 4 plus 7 all the way up to 3n minus 2, or 3k minus 2, I mean, we use k there, equals k times 3k minus 1. I'm choosing to use k because that's the letter the book uses. The book uses k. Assume it's true for some number k. That's the letter the book uses. Would I care which letter you use in the final? No, I won't care which letter you use. Pick any letter you really like. B? Alright, I'll be happy with B. Step 3. We have to prove 1 plus 4 plus 7 plus 3k minus 2 plus, what would the next one look like? 3 times k plus 1 minus 2 equals, well, instead of k, we're going to have k plus 1. And then we're going to plug in k plus 1 right there. So we're going to have 3 times k plus 1 minus 1 all over 2. So we might want to simplify that right-hand side a little bit. I'm going to write it as k plus 1. And then when I distribute this 3 through, I get 3k plus 2, correct? Because I'd have 3 times 1 is 3, 3 minus 1 is 2, over 2. So I'll simplify that right-hand side a little bit. I think that'll help. All right, so once again, to do that, we simplify. We take this whole first big block. What's that whole first big block? What are we assuming it is? K, 3k minus 1 all over 2, plus, again, I think this one, I'm going to take that 3 through and simplify. That's 3k plus 1 plus 1. That's all it is. All right, now what? I think I want to get a common denominator, so I started to write that. So that has to be a 2 down on bottom, which means I need to multiply that one by a 2. All right, so what do I have? I have k times 3k minus 1 plus 6k plus 2 all over 2. And I'm hoping I can do some magic and make it turn out to be this thing over here. Well, I've already got the 2 on bottom. The bottoms match. How do I make the tops match? Oh, God. Any ideas? Distribute the k. All right, that sounds like a wonderful idea. That's going to give me 3k squared. Then I'm going to have a minus k, but then I have a plus 6k. So the minus k and the plus 6k gives me a plus 5k. plus 2 all over 2. All right, we're almost there. The bottoms still match. What about the top? What can you do with 3k squared plus 5k plus 2? I hope you can factor it. All right. I'm going to go with it factors as k plus 1 and 3k plus 2. Why do I think that's the right answer? Because the answer I want. Now the question is it the right answer? Well, we can do a quick FOIL and we can check, can't we? So if I do a quick FOIL, I'd have k squared. Or I'd have 3k squared. That's that. Then on the outside, I'd have a 2k. On the inside, I'd have a 3k. 2k and 3k makes 5k. And then in the end, 1 times 2 is 2. So I don't really factor it. I just write down, this is the answer that I want. And then I do FOIL and check that it really did work. So you kind of cheat there. Because you know what the answer should be. So you make it be the right answer. What is the practical use of this? Wonderful question. This formula in question number 1 and this question in problem number 4, and there are other ones similar to it. There's one for 3 cubed, so on and so forth. Those formulas become very, very important in calculus when you get to something called integration, whatever that is. And then you use those summation symbols that you were talking about in calculus. Well, and then calculus is used in many places in life. So somebody at some point in the world started looking at 1 squared plus 2 squared plus 3 squared, and they recognized a pattern. And then they wanted to make sure that that pattern was always true. And so induction is one of the ways we use to prove that patterns are always true. And then, like I say, this pattern is very, very prominent in Calc 2 when you get to integration. I would not. The question on the final will look very, very much like this one. It will say, use mathematical induction to prove that, and I will actually give you the exact formula that you should have. Okay? So the problem on the final, there's one question like this on the final. It looks almost exactly like this first one. Almost exactly like the first one.
Let me guess, it's the first one.
It looks almost exactly like the first one. Perhaps more than almost like the first one. It might be. Yeah. But it's a start. It's better than a 0.